3 o'clock, so let's get started again. So hopefully we'll cover all the Python stuff finally today. So for that reasoning, the assignment 1 will be due 6 days from today, which is next Wednesday. So on Blackboard, I updated the assignment file with the new due date and also the actual date that's displayed when you try to turn in something. It shows a date there. That's updated too. So 6 days from today, so next Wednesday. And another thing, I was able to actually beat one of my minimization records, so now I got 2 bytes down, so I'm at 288 right now. So hopefully someone will actually be able to beat that, but yeah, hopefully it'll be a fun exercise to figure out what things in the actual language you can use to try to lower the byte count as much as you can. Okay, so any other questions before we return to the stuff, the lecture material? Okay. Cool. So we've been talking about quite a few awesome things like named arguments, which is that you don't have to remember the order of arguments in a Python function. You can actually permute items in the list of arguments in any order you want, and you can leave out arguments, which you can declare optional by making them named arguments in the actual implementation. So we have our example func, which has 1 required parameter, 2 that are not required, but we can explicitly assign a value to those 2 optional parameters, and they could be in any order that we want. And we can leave any number of them out if we want to. We also talked about input and output. So input just takes input from the user, so standard in, and if you want, you can write a prompt which prints the stood out, just like how print works. It takes a line of text and returns a string for you based on what was given to via standard in. We have the print function, which can take in any number of comma-separated arguments, and there are a whole bunch of named arguments which are really cool. Like you can specify the separator between the individual arguments, where all of the output is written. So you can either write to stood out, or you can write to a file explicitly. You can write what is at the very end of the print statement and a whole bunch of other things. Yeah, so we can call, say, print 1, 2, 3, have the end be ABC. A separator is space, so there's a space between 1, 2, 3, and the end will be ABC. And flush means that we'll, once we print again, the output will be erased. So it flushes the streams stood out. Cool. And we can have C-style formatting, so we can use what's called a tuple, which we'll talk about today, which you can format a particular string with C specifiers, so %D, %F, %S, all that stuff. Cool. So most of the rest of the material will be reviewed from what we've been talking about. So strings, make sure you know what string, some of the string operations. So strings can be either single or double quoted. We've talked about how they're exactly the same. They don't mean anything different. So if you have a single quoted string, you don't need to escape a double quoted string inside of it, because the single quoted string is expecting a single quote. So you can have a double quote in there fine. So you don't need to escape that. Multiple line strings, we could either have a multiple line string assigned to a particular variable, or we can use those for a multi-line comment. So a single line comment has the pound symbol. Multi-line comment, you can use a triple quoted string. Concatenation, we know how to do that from Java. It's just a plus operator. We can do repetition via the star operator with an integer. So using that, we can concatenate the same string over and over as many times as we want. We can index into a string, just like in Java. But instead of using a method, we actually use the square bracket operator, like how arrays work, because strings are basically arrays of characters. So we can index into it, and it returns us the particular string. We can have negative indexes, which is really cool. So negative indexes work from the end of the string going toward the front of the string. So let's say that string we index at -1. So -1 is the very last character of the string. -2 is the second to last character. -3 is the third to last character, and so on. Cool. Yeah, so -1 of this index is the last character, which is F. We also have slicing, which is basically doing a substring on our particular string. So in this example, we slice from 2 to 4. So the way it works is the first parameter given to the slice is where you start, the index where you start. And the second one that's given is where you end, but it's exclusive on that end. So it's inclusive on 2, but exclusive on 4. So we should return a string that contains the indices 2 and 3, which are C and D. Any questions on strings? Okay. Strings are immutable, just like in Java. We can call len on a particular string, like with any sequence, but with strings it works exactly the same. So len of a particular string returns the number of characters in it. Convert a number to a string. So you can give an integer to the stir function, which returns a string, which is that number written out. You should familiarize yourself with some of the methods. So there are some methods which are really cool, like replace. You can replace a particular character, all instances of a character with another one, or actually a string with another string. Strip is basically like trim in Java. So how many of you know the trim function in Java? So what it does is basically you remove spaces on the front and the end, and also new lines. So strip is basically doing a left strip and a right strip. So it removes all the spaces and new line characters at the beginning and the end of the string. Upper and lower are exactly what you would expect, convert to all uppercase or all lowercase. Split is exactly the same thing as in Java, so you give a particular string to split on, and it returns you a list of strings. Okay? So any questions on what some of those functions do? Okay. So lists, we've been talking about, are the mutable data structures, so they are almost exactly the same thing as arrays in Java. So some of the things you can do are you can have pretty much anything in a list. In Python, you can have any data type you want in any order you want. They don't have to be distinct, or they can be. They don't have to be the same type. So the way you write a list in Python explicitly is just using square brackets like you do in Java with comma separated values. But another way is calling the actual list constructor. So you just call list just like that, or you can specify an empty list with nothing inside the square brackets. It's exactly the same thing. Indexable, so we can index just like we can with strings. They're sliceable in the same way that that it is with strings, but in this case, we're not returning a string. We're returning a list, which contains the elements from the first index up to the second index minus 1. Okay, so it's exactly the same. So like for here, we slice from no parameter at the start, so we go from the beginning of the list up to index 4 or 3? 3, right? Because it's exclusive on the upper end. So we go from 0, 1, 2, 3, so we should have 4 elements like we do. Okay. And same thing here. We start at index 2 and go all the way to the end of the list. So index 2, not the number 2. So just a few more things on lists. So you can concatenate lists using the plus operator. So plus can be overloaded depending on the context. So here, if we have a list L and a list M, we can concatenate the lists together using the plus operator between L and M. Obviously, lists are mutable. We can assign to a particular index with a particular value. We can append a list. So the way to append is calling the .append function on a list. So here I'm saying L.append 6. So what it does is it appends it on the end of the list. Okay. Another way to do that is actually using the the plus operator on a particular value that's not a list. So if I said L plus equals 6, it'll do the exact same thing. So the plus operator for anything that's not a list will do the append operation. Okay? And yeah, anything that's not a list, yeah. But there's a way to actually, but doing the append method with a list inside will actually add the entire list that you're adding as an element. So it's like a sublist. We have the len function works the same way as strings, so we can pass in the list to len, and it gives us the length of the list. Obviously, we can have lists of lists, and lists don't have to have the same type, so we have here integers and lists, and actually we have lists that have different lengths, so they don't all have to be the same length either. So there are a whole bunch of things you can do with lists. So yeah, we can actually assign an element of a list as another list. So that's basically assigning what L is on the previous line is doing. So 1, 2 is a sublist, so we're now explicitly assigning a list to a particular index of this big list. And we can have multi-dimensional lists. So here I'm just saying the first element of L is a list, and I'm accessing the first element of that element that I just accessed. So it's the same way as in Java with multi-dimensional lists. Okay. Some other functions, some other functionalities are what I talked about with the for loop. We don't have to have just one value saying like for value in some list. We can unpack the element as we're accessing it. So if we have like complicated elements inside a list with multiple elements inside that element, we can unpack it. So here what I'm doing is saying L is 1, 2, 3, so it has 3 elements. What I'm doing here is I'm assigning to 3 separate variables at the exact same time. So I'm saying A, B, C is equal to L, which means that I'm unpacking the list. So the first element of L goes to A, second one goes to B, third goes to C. And so this actually always works if you have more than 3 elements too. It just happens that the first 3 will be assigned to A, B, and C. Obviously, if I have fewer than 3 elements in L, then C won't be assigned a value, and so it'll throw me an exception. So the number of arguments on the left has to be covered by the right-hand side, but you could have more on the right-hand side if you want. Yeah?
So what would happen if you had a 1, 2, 3, 4 in L, and you just had ABC? So ABC would get 1, 2, 3.
Yeah.
What would happen to 4? It just wouldn't get assigned.
It just wouldn't get assigned. So let's just see that in action. So let's run Python 3. So let's say that our list is 1, 2, 3, 4. A, B, C is equal to L. Oh, never mind. I guess if you have more than the number of arguments, then you won't get assigned correctly. So you'll throw an exception. I'm not sure why that is, but maybe if it's a tuple. No, I don't think that'll work either. Yeah. So apparently I was wrong. You have to have the exact same number of arguments on both sides. Yeah, that was my mistake. So you have to have the same number of arguments on both sides. So common operations, like I just said, you can append to a list. And it appends at the end of the list. There's a really cool function called extend. So when I mentioned append, I said that if you are passing X as a list, it adds the entire list as one element of the big list. But one thing you want to do sometimes is to basically copy the elements over, to like keep adding more elements to this big list that I'm adding to, which is L1. So what extend does is basically that. It copies everything over to extend the list, basically. So it's kind of like concatenation. Actually, it is exactly the same thing as concatenation. So, but it's just explicitly said here that it's extending a particular list with another list. Okay. We have insertion at an arbitrary index, so we say insertion of I, comma x, so I'm inserting at index I with the value x, just as you would expect. Removing x, you just remove the element at the first occurrence of x in the list, and if it doesn't exist, it'll throw an exception because it's trying to remove something that doesn't exist. L.pop, so how many of you know what a stack is? So yeah, so you know what a stack is, you push and pop off the stack. So it kind of works the same thing here, you just pop off the last element. But you can also specify a particular index I, so it'll pop off that particular element. Okay? So you can easily model a stack this way. So push is like append, and pop is pop. So yeah, we have a clear method which clears the list. Some other operations. So a really cool one is index of a particular element. So it'll return the first index of x in the list. So you don't have to do like a for loop and then have a counter for when you hit the element and then get out of the loop and all that. So index takes care of that for you. It'll return the index of x if it exists in L. L.count, so here's another cool one. It'll count the number of occurrences of x in L, which is quite useful if you have a really long list and you don't want to like create a for loop and all that. You just want one particular method that does it, and count does that for you. L.sort does a sort in place. L.reverse, I think it reverses in place. Let's see. So let's say L is 1, 2, 3, 4. L.reverse. Yeah, it does it in place. Yeah, so there are some methods that will return you the value and some that will do it in place, like sort and reversed. And reverse will do it in place, but there are some other methods like sorted and reversed that will return you an iterator to the reverse thing. So if you have like a small list, then reverse is more efficient because it'll just return you the entire list. But if you have a really long list and you don't want to make an entire new list, then you would use reversed or sorted for that. Okay? Yeah, because what they do is instead of making an entire list, they return you an iterator, so it'll return you the first element, but that's it. And then when you ask for another element using the for loop, it'll return you the next element, then when you ask again, it'll return the next one, and so on. So it actually doesn't use a lot of memory. Okay? We did reverse. L.copy returns a shallow copy of the list. So what is a shallow copy? Versus, say, a deep copy?
Non-permanent?
It's kind of like permanence. So so how does, like, say, a string work in Java? What are you really accessing when you say, like, A equals B, like you're copying the string over to A? Like, if B is a string and I'm copying it over to string A, what am I actually doing?
Creating a new string.
Well, I'm making a new string, but what am I actually copying over?
Character location.
I'm actually not copying the characters over, like, saying, yeah, I'll just do it. So like if I do string B equals hello, and then string A equals B. So what this does is, how is B stored on the computer in the memory?
Some address.
Yeah, it's stored at some address. But when I access the actual word B, what am I doing?
A is a pointer.
Yeah, so B is a pointer to a character array, which is the characters HELLO. So when I'm actually copying over here, I'm copying the pointer over. Okay? So what this is a shallow copy. So a shallow copy copies the pointers over. It doesn't actually copy the elements over. Okay? So it works pretty much always the same way, but there are some contexts where you actually do need a deep copy versus a shallow copy. And you may imagine that a shallow copy is a lot more efficient because no matter how large the string is or the list is, the address is fixed in size. So no matter how large the list is, doing a copy of a particular address is very efficient. So that's why sometimes if you do need efficiency, a shallow copy is better than a deep copy. Okay, so any questions on everything we just did with lists? Yeah. Oh, I didn't hear.
If you do a shallow copy, and if you change the original list, then the copy list will also change.
Yes, because they're corresponding to the same memory location because they're both pointing to the same place. Yeah.
If you do a deep copy, it won't change.
Yeah, it'll actually change both lists then. Actually, let's do that as an example. So if we do L is 1, 2, 3, 4, 5, and let's say that we assign M the list L. So this will actually let's just do it as the method here. So L.copy. So M is there, L is here. So if I say L of 2 is 100, if I print L, the second index is obviously assigned 100. But if I I think that should work though. Okay, yeah. I thought L-copy actually did a. Let's see. Let's copy Python because the documentation actually says that it does a shallow copy.
You would think it would change.
Yeah. Yeah. Huh. Well, anyway, the copy operation is basically the same thing as the assignment operator. So what that does is it assigns the pointer of the list. Oh, I know why. It actually does return a shallow copy, but how are integers stored? Do they have that pointer business? No, they're actually stored with the actual value there instead of a pointer. So if we actually amend our example with strings instead, I'm pretty confident it'll work. So let's say M is L.copy, and then M and L are the same right now. So let's say L of 2, L of 1 right in the middle of the list is 100. Oops. So if we print L, is that? Oh. Apparently the documentation's not right. I'll take a look at this and I'll post on the Google group why that's not true. But it says it does return a shallow copy of X, so I'll figure that out. Again, don't do live coding demos. All right, so yeah, any questions about lists? So to answer your question, an assignment actually does a shallow copy by copying the list pointer itself. Okay, so I guess I didn't have the animation well. Dictionaries we covered them, are key value pair mappings. So we have these unique keys. So the keys are unique, but the values don't have to be unique. And every key is assigned a value. So it's just a mapping between a key and a value. One application, as we'll see in a second, is counting the number of each character in the string. So what you can do is you can loop over every character in the string and check if the character you're currently looking at is in the dictionary. If it is in the dictionary, then we've seen it before. So what we do is we increment the number of occurrences of the character by 1. So let's just do this as an example. So let's just do this as example 1 dict. So let's just say we have the string awesome. And so I want to count each of the characters in the string. So like for the space character, I see it twice, so I should see 2 at the end. So the way to make a dict is the same way as a set, but the way we interface with it is different. So the way to create a set is with open, close, curly brackets. Another way I can do it is just calling the dict constructor by itself. And that'll actually do the exact same thing. So what I want to do is I want to loop over every character in the string and then do something with the dictionary. So for character in A. So what I want to do is I have 2 cases. I have one where I've seen it before, in which case I increment the number of occurrences by 1, and otherwise I've never seen it before, in which case how many times have I seen it now? Well, I'm now encountering the character, so now I've seen it once. So I should set it to 1. So the way to get and set a value for a dictionary is exactly the same way. So the way to do that is for a particular character, you just use the square operator, just like for lists, just like for strings. But here, using the square operator will access the value assigned to the thing in the square brackets. So it doesn't have to be just a number now. It could be any possible key will be inside the square brackets. So the way this dict is going to work is the keys are each of the characters in the string. Characters in string. And what do you think the values are going to be corresponding to each key?
It's placed.
Well, I want to count the occurrences of each character. So it should be it'll be the integer which will be the number of occurrences of that character in the string. So the value are the number of occurrences of each key. So I should expand this a little. So for each character in A, I have 2 cases. So I want to check if the particular character is in the dictionary, right? And then if it is, I increment the number of occurrences by 1. If I haven't seen it, I actually set the number to be 1. So the way to check if a particular character is in the dictionary is the same way as checking if something's in a list or if it's in a set or something like that. So if character in D. So if my character is in the dictionary, right? And so if it is, then I increment by 1. So the way to interface with that is call D of character. So this will access the value associated with that character key. So what do I do now? Plus equals 1. There actually isn't a plus operator in Python. I know, it's so sad. Yeah, but you do plus equals 1. And then otherwise, so if most people, when they start working with dictionaries, actually just do this. So what's the problem here?
Character may not be in the dictionary.
Well, if I wanted to actually assign a value to a new key in the dictionary, I actually just say D of, say, A is equal to 1. I just assign. So this will create the key A, even though it hasn't been existing before. So
The value is none.
yeah, the value is none. It's not defaulted to 0. So if you try to add 1, it'll actually give you an error. So we need to do the check first to check if it's in the dictionary. If it is, then we must have assigned it an integer value so we can increment it without a problem. But here is the crucial part. Else, well, now we haven't seen the character ever before, so now we got to make sure we assign an integer, which will be 1. So D of character is equal to 1. Okay, so this will directly assign 1 to as the value of character if we've never seen it before. Otherwise, it'll add 1. And so now I want to view the results, so I just print the dictionary. So print D. How many lines do you think you would have to do this like in Java or C++? It sounds painful, doesn't it? Yeah, so it's just really cool how this is so simple. So let's just run it. So Python 3, example 1. All right, so there's actually a nice module called PrettyPrint in Python. I think, yeah, it's called pprint for PrettyPrint. And what it does is it prints data structures in a nice way so it's easier to read than this. But we can actually read this just fine. So what was printed, it says that the key M was assigned 1. So that means we've seen the character M one time. And let's go to a non-trivial one. The key S, so the character S was assigned 2. So we've seen the character S twice, so we've seen it here and here. Why? Because dictionaries are, the way they're implemented, are unordered. The way, if you actually look at how it's actually done, is unordered because that's the way in order to guarantee constant time lookups.
So it was saved in memory unordered.
Yeah, so there are actually, if you go to the, what was it? The collections module, there actually is an ordered dictionary. So if you go to the collections module, there is a subclass of dict called order dict. So what that does, it remembers the order of elements as they're added to the dictionary. And you have some other ones like counter, which is basically for counting objects. So that's basically what we just did. So we could have just passed the string into counter and it will do the exact same thing. Another cool one is default dict. So we talked about that problem where the value was assigned to none. But for default dict, you can actually give it the default argument. So when a key is created, the value is assigned to the default value that you pass into it. So there are quite a few awesome things in Python, especially some of these are unique to Python 3, so have fun playing with this. But counter, order dicts, and default dicts are some of the most common things in this module. But any questions on that example for counting things? Okay, so to loop over a dictionary is just to, actually we're not looping over the dictionary, we're looping over a character. So what if I wanted to say loop over the dictionary and print each of the keys and values corresponding to it? So you may think, well, there are two options here. You can either loop over the keys or loop over the keys and values at the same time. So in that latter case, you would return a key value, both of those values at the same time. So you can do that unpacking thing we talked about. But the way it's actually done is you just loop over the keys. So for K, I can actually just call it key. For key in the dictionary, what I want to do is I want to print the key itself and the value associated to it. So how do I look up the value of key?
Dictionary and then key.
Yeah, so D of key, exactly. So print key and maybe like a arrow operator just to show that the key is assigned to and D of key. Okay, so let's try that. So now it's a lot nicer. So note that it's not in order because dictionaries by default are unordered data structures. So it'll print the things as necessary. Okay. So any questions on dictionaries? Okay. Let's see. So we covered that. Keys and values can be of any type. As long as keys are not none and are unique. If I try to assign a key that already exists, as we actually did in our example, it'll just either override the value that exists there or update it or something like that. Okay? Yeah, cool. So collections, like I just showed you some of the cool things in the collections module. Collections is a module. So one useful data structure sometimes is called a deck. So it's not a DQ. It's a, although I kind of want some DQ right now. It's a deck. So how many of you know what a deck is? Not a deck of cards, but a computer science deck. So what that stands for is double-ended queue. Okay? How many of you know what a queue is? Yeah, so for those of you who don't know, it's you can the way it works is first in, first out data structure. So what you do is you end queue at the back of the queue and you pop off elements off the front. So you're inserting at the back of the queue and popping off at the front. Whereas for stack, you push and pop at the same location. Okay? So for a deck, it's basically you enqueue and dequeue on both sides if you want. Okay? So yeah, so it's just a double-ended queue. Use it as a standard queue. So what you can do is you can create a deck, and you can call some methods on a deck, which are like append left. So it appends on the. You can call it the left. It depends on your perspective, but you can append on one side or append right if you wanted to. You can call len, append left, a whole bunch of other things you can do with that. So a deck is useful for some contexts. Pop, you can do the same way. So it's basically like a DQ. Another one is counter. So that was basically the example that we did, but it's an actual class that you just pass in a particular sequence to it, and it'll do the counting for you. So yeah, obviously it counts things, and it counts the occurrences of each element within the sequence that you give it. So obviously it's just a dict in disguise. So here I can I can call the counter constructor and pass in the sequence. In this case, it's abracadabra, a string, and it'll count the occurrences of each element in the sequence that you're given. So here, since each element is a one string character, string of length 1 in this string, so it'll count A, B, R, C, and D. So those are the values the keys that you should see. Actually, let's just do that as an example. So since this is in the collections module, I obviously have to import the collections module. So if we import collections, and then now I do C is counter of abracadabra. Oh yeah. So since I didn't do that from collections import counter thing, I have to reference the module name. So collections.counter. So if I try to print C, it'll tell me that it counted the number of occurrences of A, B is 2, R is 2, D is 1, C is 1. Okay? So it's just a really easy way to do counting over a particular iterable. So this obviously works over not just for a particular sequence, but you can actually also pass them as named arguments. So, and they can actually be arbitrary named arguments here. So let's just say we do the same thing, but with these named arguments. 3 10s, 1 2 3 4 5. So it can actually do this over an arbitrary set of named arguments too. So even though I passed these as named arguments, they actually converted them to strings. So like you see CSE294 and CSE310 in the constructor are named arguments. And when I printed it out, it actually printed them as keys, which are strings, which I think is really cool. So you can actually, in Python, handle arbitrary keyword arguments, named arguments. Okay? So any questions on those things in the collections module? Okay, cool. Tuples, I've mentioned this before, but what a tuple is just an analog of an array, of a list. But the only thing different here is that the elements are immutable. So you can't change them, you can't update them, but you can access them. And they're separated by commas just like lists are. So in the way that they're written are with parentheses. So you can do, that should be tuple unpacking. But Actually, no, it's not. Tuple packing. So, like when we talked about unpacking a list, so we have a list on the right-hand side and elements on the left-hand side, and we unpack the list. But here we do what is called packing, which is basically you have an arbitrary number of arguments on the right-hand side, and one argument on the left. And what that does is it creates a tuple on the right-hand side, and T here now is a tuple, which corresponds to the tuple 1, 2, 3. Okay. Just pretty much for all sequences, you can do a len on this. It's indexable, so you can say T of 0. It works the same way. Also multiple types, nested iterable, so you can do pretty much exactly the same thing as a list, but the only thing different now is that obviously, since it's at least one object, is non-empty, and is immutable. So you can't update any elements, and obviously you can't add elements to a tuple. Okay? Yeah.
So why use that over a list?
Right. So why use it over a list? So in context where you don't want to update elements by accident, or you don't want to add elements by accident. Yeah. Yeah. Okay. And I think you can actually have multiple tuples and work with them pairwise, component-wise. So like if I have another tuple, say S is 4, 5, 6, I can work with each of the components, like 1 and 4, 2 and 5, 3 and 6. So it's just easier to store them this way because you know that they're going to be exactly the same length, for example, and you know that they're not going to ever be updated. Okay. So any questions on tuples? Cool. And there's actually something called name tuple, which is I didn't think I was going to do this, but name tuple is really cool. So it's also in the collections module. So when I index into a list, I obviously have to specify an index that I want to index to, say like 0 or 1. But wouldn't it be really nice that I can give names to each of the indexes? Like I could say the first one is, say, luminosity, and second one is, I don't know, fluorescence or something. So you can actually give a name that you can look up as a data member. So what name tuple does is basically you construct a tuple which has a name with it and a list given to it, which is the elements of the tuples that you're going to make with it, the name tuples that you're going to make, with each of the element names corresponding to it. So instead of saying like T of 0, I can say T dot luminosity, like in actual code, like not even as a string anymore. So name tuples make things a lot easier to read, but it works the same way as lists, but lists don't have this functionality because they're updatable, right? Because for name tuple, you can have, since they're always the same length, you know that you can assign a name to each of the positions in the tuple. Okay? Cool, so tuples, we covered that. Sets, what's a set again? Oh, what's that? Yeah, so it's just a collection of items that are unique. So you can't index into this because it's an unordered data structure, but the cool thing is you can mutate items in it. Because obviously you can add items and delete items because it's a set of unique items. All right, so the way to write a set is the same way as a dictionary is, but the difference here is that I don't index into the set with a particular element, which is the key. Here I just say like set.add. So there's no square brackets operator for adding things, unlike dictionaries. But here I have two sets. One set has the elements 1, 2, 3, and the other set has the lowercase characters A through Z. So each of these is unique, so they're both sets. So you can create an empty set with set, or you can do the same way as with dictionary with two with two curly brackets. Yeah. You can create a set with values directly, just like you can do with list, but that was with square brackets, but here is with curly ones. Obviously, we can't index into it. So the only way we can actually test if an element is in the set is saying if value is in the set. So if value in set. So you can test membership. How do I test if something's not in the set? Yeah, not in. Yeah, it's exactly the same thing. Iterable, so you can just say for x and s, just the same way as you can do with if, but now the x is going to be iterating over the elements in the set. And you can't guarantee order, obviously. Yeah.
You do exclamation point in or not in?
No,
Or is it not?
NOT space IN, yeah. Python tries to be as much as English as possible. You might be able to do this exclamation mark, but I'm not sure about that. But it's certainly not what will work. Some operations, you can do a len on it to obviously test if the element's in the set, not in the set. One that's really cool is checking if two sets have nothing in common at all, and that's what's called having the sets be disjoint. So calling is disjoint on two sets will return true if there's nothing in common between the two sets, and obviously return false if there is some element in both of the sets. So here's another example of overloading operators. So less than or equal to says that every element of S1 is in S2, so it's a subset of this set. Less than but not equal says a proper subset. So what that is every element in S1 is in S2, but there are some other things in S2 that are not in S1. So they can't be equal. S1 vertical bar S2 just returns the union. So what it does is it creates a new set, which is basically adding every old element in both of the sets into this giant set. So it returns the union. So every element in the union is either in S1 or S2 or both. S1 and S2 returns the intersection, a set which contains all the elements that were originally in both of the sets. So it's almost the opposite of the union operator, but here it's just doing the intersection, which is both elements that are in both of the sets. Set difference is basically every element, returning a set that has every element that's in S1 and not in S2. So, so what this is effectively doing is S1 minus S2 is equivalent to saying if X in S1 and X not in S2. So those two things are equivalent, but what this does is actually returns you the set of the things that have this property, that are in the first set and are not in the second set. Okay? So any questions on these first set operations? Yeah, so a union is basically the equivalent operation of making a set and adding all of the elements in both of the sets back into this set.
To S1 in this case.
Well, S1 or S2 will actually return you the set. It doesn't add it to S1 or S2. It returns you a new set separately.
Gotcha.
Okay? Actually, all of these are true for these three operations. Okay? Any other questions? Okay. Some other ones, a shallow copy of S, which we know now is a deep copy. S.addX, so the way to add things to a set is calling the .add function and passing in the element that you want to add. So if it's not already in S, it adds it obviously to S. If it already is in S, then it basically just does nothing. Okay, because it can't have duplicates. S.remove X, so if X is there, then it removes it. If it's not, it will throw an exception because it's trying to remove something that doesn't exist. S.discard X, but no exception. S.pop, so obviously, since we can't index into a set, there's no way to remove, say, the last element of a set, so it just removes an arbitrary element. Sometimes that's necessary for when you want to just pick an arbitrary element, so that's an easy way to do that. S.clear, like for lists, is just the same thing as making the container empty, and that's it. So, any questions on the Python stuff? Yeah. Oh, what's that?
How can you use collections over two areas?
You use collections over what?
Boolean arrays?
Collections, I'm not sure what that means. You're using
2D
collections.
arrays.
Oh, the 2D arrays? Or Boolean arrays?
Yeah, like a packet. If it's a string of strings, the collections work on them.
Like what example do you mean?
It's a paragraph of text. It will not be a single string. It will be different lines in a 2D array.
Like what operation do you want to do on that?
Creating the dictionary, equivalent to dictionary using collections. You showed collections where we could compute the letter frequency.
Well, len just works on any string, so it doesn't matter the length.
But here it's not a single string, it's a string of strings.
Oh, yeah. So if we had, say, let's just do this as an example. So if we have a list which has 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a list which has different length strings in it, right? Right? So what you're trying to do, I think, is to print the lengths of each of the strings in there, right?
No, the frequency of each of the characters.
Oh, okay. So what you could do is you can loop over this list and then do a counter on each one. Okay? And just print a new counter. So like for string in L. So what the 3 dots mean is that it's expecting that you're going to be indenting here. So for string in L, I can do a print collections.counter of string. So it'll do a counter of each one. Right, so like the first one counts the first string, second one counts the second, third one counts the third. Okay? Oh, sum. There's a way to, so there are 2 things you can do. There's one which is concatenate every single thing in the list, which there's a way to do that. So if we have L, which is this, you can write a string as, so there's a method called join. So what that does is it's a string dot join a list. So what that is between every single element of this list L, insert this string. Okay? So if I want to count everything, basically concatenate this entire string together, I don't want anything in between adjacent elements. So this string is going to be the empty string. So if I do that, S is just the concatenation of everything in the list, right? So now I can do print collections.counter of S. And then it'll do the entire thing, which is equivalent to adding everything all at once. But there's, I believe there is a method for doing this explicitly. So if we go to the counter doc, you can do the plus equals operator. So if we do the same thing, so like we have C is equal to collections.counter. So here now I'm just making an empty counter, and then I'm going to update it over and over for each element in the list. So I make a counter. So for every V in L, I'll just give it a name, every string in L. So now I want to add to my existing counter C. So C plus equals, now I'm going to make a new counter, which will be the counter for the string that I'm currently looking at. So collections.counter of string. So now if I print C, it prints the same thing. Okay? Does that answer your question? Yeah, so there are methods that will do this explicitly, but there are operators which are overloaded to do these. And most of the collections work that way, yeah.
What did the S equals the dot join now?
Yeah, so just to recap what join does, it in the parameter it takes a list, so and you basically do it over a string. So a string.joinL, and what that means is between every element of L, insert this string there. Okay, so what I did is
that a space there? Or?
it's an empty string.
Okay.
So if I go back, it's in fact an empty string. But I can do a space if I wanted to. So if I print S, now it has a space in between.
Oh.
But I can actually put anything here, like 3 underbars, and it'll do the same thing. Okay? So any questions about any of that? So I think we should take a short break, and then we'll continue a little bit after 4, and then we'll start the algorithm stuff. All right? Cool. So we're ready to finally start new material. So get into the basic structure of algorithms and understanding the core component of the class, which, I mean, the first word of the class is algorithmic. So we probably should cover algorithms at some point. So what is an algorithm?
Set of specific instructions.
No, I think it's this. Worst pun ever, right? Right. But really, what's an algorithm? It's a set of it's a set of procedures that does something. But can we call an algorithm if it runs forever?
Sure.
Well, in the literature, it's actually called what is called a procedure. But algorithms, we want to make sure that they run in a finite amount of time. Okay? And there is some deterministic specified order that things are executed. So it's not just say, pick a random line to execute, then jump to that line. It's an actual specified order that we execute things in. There's some entry point where it's well defined where the algorithm starts. So again, it's not just start at some random place, that there is a specified entry point. And as you imagine, there's an exit point also where the algorithm ends. And algorithms have some inputs, either no inputs at all, or some inputs, and it produces some output based off the input, right? It follows those steps in some order, and it produces some output based off the input. And so how do we represent an algorithm? What we do is we use programming languages. But what if we wanted to abstract away from programming languages altogether? How do we usually write algorithms down? Either math or more generally? Which is usually called? Like an English set of instructions?
A recipe.
Like some recipe, or if we want to mix some code in with it, it's called pseudocode. Right, return pseudocode. So pseudocode, pseudo means almost. So it's almost code, and it's actually really cool. I've mentioned before that pseudocode that I've written for these slides are almost exactly the same thing as Python, so I actually wrote most of these in Python. So it's actually really nice that it's so close to being implementable. That's one of the key features of Python and languages like it, that you want pseudocode to be as close to programmable as possible, but be able to express what the algorithm's trying to do without trying to get into the semantics of a particular language. So it's a mix of programming concepts and English language. So it's easily readable and easily implementable at the same time. So you want to communicate ideas in the algorithm without actually having to worry about the details of the said programming language. And there are levels of pseudocode, so we have high and low level pseudocode. So I have some examples here of some pseudocode. So the first one is display all prime numbers less than 10,000. Anyone not know what a prime number is? Okay, everyone knows what a prime number is. So do you think this is a high or low level pseudocode? It actually really does depend on your perspective, because someone said high, someone said low. I think that this is a little bit of a high level pseudocode because it doesn't actually use some programming language constructs here, unless yeah, yes. So higher, low level, we mostly agree high. What about this one? For every integer between 2 and 10,000, if it's a prime number, then print the number. So is that high or low level? Again, it depends on your perspective. It's definitely less high level than the first one, but it's not quite to the level where we can say, oh, there's some programming construct in there. It's easily implementable. Because we know the first part of that sentence for every integer n between 2 and 10,000. We know how to do that with a for loop. But we don't know, although we probably have programmed it before, but it's not clear from here how to implement n as prime. Okay? Although we do know how to print it, but there's some parts of it that we don't quite know how to program directly. So higher, low level, I think somewhat in the middle. It's not quite low level, it's not quite high level yet. How about this one? For n set to 2 to 10,000, do if prime, where prime is a function, and output n. So do you think that's high or low level? That's definitely more low level than the previous two. So how to implement this? So how do we implement testing if a number is prime? Well, what's the definition of a prime number?
Divisible by itself.
Yeah, it's divisible by itself and 1. Those are the only divisors of that number. So an equivalent way is saying every divisor between 2 and n minus 1 is not divisible by n. Or n is not divisible by anything between 2 and n minus 1. Right? That's equivalent to say that. Unless the number is 2, obviously, in which case it's prime. But so the idea is to just use a trial by division algorithm for a given number. So what we do is we just assume that the number is prime at the start, and then what we do is we search through the list of candidates for a particular divisor. If we find a divisor for which we show that it's divisible by that divisor, then we say that is prime is false. So because we found that divisor that we were searching for. But if we don't find one, then we default to true. So if n is even and is not 2, so what should I say here? If n is, it's definitely not prime, right? Because if it's even, it's divisible by 2 already. And if it's not 2, then it can't be 2, and there are no other even prime numbers. So it definitely must be false, and we must stop, right? Because there's no point in searching further. But what if, so at this point, if we're still searching, the number is either 2, in which case we wouldn't even do anything of this for loop, right? Or the number is odd. So what we do is we search through the list of candidates. We already tested 2. So the next candidate is 3 through n minus 1. So what we do is, if this divisor divides the number, then we just found the one that, the example for which shows that the number is not prime. In which case, we report that as not prime, then stop. Then at this point, if our flag variable is true, then we print that particular number, right? So this is a primality test for checking if a given number n is prime. So how do we get back to our original problem, which says print every prime number between 2 and 10,000? So how would we implement using that prime checker that we just made to check for every single prime number between 2 and 10,000? Well, we can just iterate through from 2 to 10,000. So just for every integer between 2 and 10,000, what do? What we just made the previous slide. Yep, and then we're done. So So you can see here that we're actually writing English, but it's very close to what Python is, to what a programming construct is. So that's one of the hearts of writing actual pseudocode, is to make sure that you can implement the algorithm easily, but also understand what the algorithm's doing at the same time. So that's one of the hearts of algorithm design, to be able to handle both of those at the same time. Okay? Cool. So our algorithm was quite long. It was on 2 separate slides. So how do you think we should handle this? How do you actually do it when you code? Like if a function gets pretty long, what do you do? Make more functions, exactly. So we split up the code into more functions that are short. And so there's actually no standard for what simple or short is, but usually if you can fit it into a slide, that's pretty short. But it obviously depends on the implementation, the programming language, things like that. And the functions obviously should do one task. They shouldn't be doing too many things at the same time. Because if you do only one task per function, then you can easily delegate the work. You can figure out, this function does exactly this, and I don't need to think about anything else. It does exactly one thing. Why would you want to do that? Why would you want to split it up into this way?
Parts that are probably going to be repeated.
Right, right. So there are going to be parts that are being repeated. And we can, if we want to add more functions, let's say, then because we split this up easily, then we can call those existing functions if we want to. So we can basically delegate the work and make future proof of making other functions easier to implement. Once,
Makes your code more readable.
right, exactly. It makes your code more readable. Exactly. Reusability, so we can reuse components. Readability, because the functions aren't too long. And accuracy, because since the functions aren't too long, we can find bugs more easily. Okay. So how do we test if an algorithm is correct? Yeah, exactly. So what you do is you provide inputs and sample outputs. Like for assignment 1, I have some sample input, sample output, and then we just check if the input matches the output. Actually, something that's really cool, you'll find that it's impossible to actually figure out whether an algorithm is 100% correct just by checking inputs and outputs, because there are infinitely many values to check. But we can get a feel for whether an algorithm is correct by checking some number of inputs with some number of outputs. So how would you go about testing a particular program? So like you're given us a piece of code, how do you test it?
It depends on what it is, but usually you test like a middle value of bounds, an inner bounds and an outer bounds.
Right, so you would test some kind of bounds on whether things are checked. Like for an if statement, if I'm checking against a specific value, I check right on that value and some values right around it, right? So I check boundary cases of all of the conditions within the particular method or the entire program. Okay, so some good heuristics. So for our example, what we do is we check the bounds. We are working with 2 to 10,000, so I should check the bounds, 2 and 10,000. If 2 says yes and 10,000 says no because 10,000 is even, then that's a good heuristic. Test all possible paths. So I think this is what is called the cyclomatic number for a particular program, which is basically all the number of possible paths that can go through the program. So like obviously for an if statement, you can either go into the if statement or not go into the if statement. So all the possible paths, just test each one. If each one succeeds, then that's another good heuristic. So let's analyze the inner loop of our prime program, which is that prime checker part. So how do we do that? We come up with some test cases. And so why is this sufficient? Why would it be sufficient just to test that middle part of the program? The prime checker part, not the loop part.
Because if the prime checker is true, then everything else is true.
Exactly. If the prime checker works, then we know that the loop will work because it's just a counter from 2 to 10,000, and we've already checked the smallest and largest number. So we know since the smallest and largest work, then if everything else works, then we know the entire thing works. So that's another good heuristic. If you know a partition, so anyone know what a partition is? So a partition is basically splitting up a particular thing, like a set or a program or something like that, into disjoint parts. So each of the parts is completely disjoint. There's nothing in common between each of the parts. So if every single partition, if you make a partition of your program, and each of the partitions you know for sure will work, then the entire thing must work, because each of the partitions covers the entire program. Okay, so let's look at some test cases. So our first test case will test the smallest prime number, and we should output that 2 is prime. It's the lowest one. So now we're just going to test some other ones in the middle range between 2 and 10,000. And 100, we should output that 100 is not prime because it's a even number. Another one, 50 is not prime, 23 is prime. And we can make more test cases, right? Obviously, the best test case is to have a test case for every single number, right? But that would be kind of exhaustive, right? I don't want to write is prime, not prime for nearly 10,000 numbers. So what we do here is we try to write the smallest number of test cases we can so that we are guaranteed to get the right outputs for every other number we don't test. So that's actually the art of testing, being able to cover all possible, or as many as possible numbers, or the outputs that we want, using as few test cases as possible. And that's actually some of the research that I like doing, is finding the smallest number of tests for a given program. Okay, just one more thing, and then we can take off. So brute force algorithm is we're testing the primality part. We're not dealing with the for loop part now. We're just doing the middle part. So I wrote is prime BF for brute force. So it takes a number n. So we have that variable is prime is true that defaults to true, and then we check if the number is even and is not 2, then we return. We can actually just return false there instead of setting the flag variable directly, but this also works. Otherwise, then we check between 3 and n minus 1. Why did I not write n minus 1 there?
Because it doesn't include that amount.
Right, so because all ranges in Python have inclusive lower end and exclusive upper end, so this goes to n minus 1. Then we check if d divides this number that we're given, then we just found that divisor that we were searching for, so we set it to false. And then we return the flag, either it's true or it's false. Okay? Any questions on that? And so what we'll get to is optimizing this program, optimizing the algorithm, then trying to analyze the algorithm, how efficient is this algorithm, and then we'll get to other algorithms next time. Okay? So any questions about anything we covered today? Yeah.
Not really on what we covered, but could you post these slides so
Yeah.
I would like to take notes on the slide?
Yeah, absolutely. I'll post them. Any other questions? All right, cool. Have a good 4-day weekend.